Good afternoon. With pleasure, I present our work, New Organic Semiconductors based on metallophthalocyanines and pyrrole derivatives theoretical study. This work was done by Giovanna Angelica Vázquez Hernández, Modesto Javier Cruz Gómez, Maria Elena Sánchez Vergara, Roberto Salcedo, and myself, L FOMINA. In the Universidad Nacional Autónoma de México, el Instituto de Investigaciones en Materiales. Phthalocyanines are a versatile and robust class of compounds. These compounds are in their metal derivatives have recently attracted increasing interest not only for the production of dyes and pigments, but also as building blocks for the creation of new molecular materials for electronics and optoelectronics. Some of these applications include the use of gas sensors, solar cells, liquid crystals, and inorganic semiconductors. Most of these applications are associated with the large and flat p-conjugation system of phthalocyanines, as well as the type of central metal. This system of delocalized electrons in the main structure facilitates the transfer of charges inside it. The structures of phthalocyanines can be modified by introducing groups or molecules to peripheral and non-peripheral parts of the aromatic rings, which allows it to provide different characteristics in terms of its electronic behavior and create N or p-type semiconductors. In this work, organic semiconductors based on metallophthalocyanines with metal centers cobalt, iron, and zinc were functionalized with barrel by diazonium salt reaction. Theoretical calculations were carried out by applying the FT method based on the combination of back gradient correction for exchange and Perdue banks for correlation. Calculations were performed using the 631J basis set. Theoretical calculation demonstrated that the derivatives of metallophthalocyanines manifested a semiconductor behavior with compound with metal center iron being the one with the lowest Eg value 2.02 electron volts compared to compounds with metal center cobalt 2.13 electron volts and with metal center zinc 2.09 electron volts. Evidently, they form the donor-acceptor structure due to distribution of their electrons, which are concentrated in the four parallel substituents HOMO, whereas in the center of the molecule, where the metal is located, neutral LUMO, favoring the flow of electrons from the periphery to the center of the complex. We can see the steps of synthesis. The first scheme shows Glaser-Hay reaction, the second Rice-Schultz reaction, and third reduction of nitrothermine compounds. Scheme 4 shows reaction of diazonium salts to obtain the derivatives of metallophthalocyanines. Due to the aromatic nature of the ring, which supports the substituted pyrrole group, a variety of isomer products are possible. However, calculations were carried out on the isomer which bears the pyrrole substituent in parallel position with respect to the non-boring phenyl ring. Therefore, in all cases, the structure of the calculated species is presented in figure 2a. This structure belongs to the C4H point group in a frozen situation. The analogies for the structure containing cobalt, iron, and zinc were calculated. Semiconductor quality should result from the combination of the frontier molecular orbitals derived from the two kinds of organic fragments which constitute the complexes. Analysis of this frontier molecular orbital yields a clear answer to this phenomenon. Figure 3 shows the shape of HOMO-LUMO for the complex of zinc. Both functions are double degenerated sets. Indeed, HOMO is the combination of two degenerated sets which encompass four single orbitals. In the present analysis, the important factor is the source of the short band gap, as apparently the entire HOMO is concentrated on the chiral terminal groups, whereas the LUMO is focused on the aromatic set around the metal atom and the phthalocyanin framework. The combination of these functions facilitate electronic flows from the periphery to the center of the complex. The electron's presence on the terminal chiral groups is reinforced by the molecular electrostatic potential mapped onto electronic density. The most important feature to consider of these molecules is their semiconductor behavior. The calculations show band gap values of 2.13 electron volts for the cobalt phthalocyanin sample, 2.02 electron volts for the iron analog, and 2.09 electron volts for the zinc molecular material. This feature should be highlighted because it has been reported that the chiral units alone average 4.6 electron volts. These results are presented in Table 1, which also summarizes the values obtained for the frontier molecular orbitals HOMO-LUMO for the three molecular materials. Table 1 presents a comparison between the EG obtained experimentally and the theoretical band gap. Conclusions. Molecular materials based on metallophthalanes with metal center cobalt, iron, and zinc functionalized with 1-para-aminophenyl 2.5-diphenyl chiral were obtained by implementing a diazonium salt reaction. Theoretical calculations demonstrated that the derivatives 3ABC manifested a semiconductor behavior with compound 3B, metal center iron being the one with the lowest EG value, 2.02 electron volts, compared to compounds 3A and 3C, metal center cobalt and metal center zinc, respectively. Evidently, they formed the donor-acceptor structure due to the distribution of their electrons, which are concentrated in the four chiral substituents HOMO, whereas in the center of the molecule, where the metal is located, it remains neutral LUMO, favoring the flow of electrons from the periphery to the center of the complex. Here we can see the references. Vázquez Hernández would like to thank Dirección General de Asuntos del Personal Académico, Universidad Nacional Autónoma de México, for postdoctoral fellowship. We are grateful to Tejeda for XRD analysis, Canseco for diffuse reflectance measurements, Del Villar Morales for NMR spectra, Reis Morales for technical assistance and support in thermal analysis, Bazan Diaz for SEM and EDS analysis, Gracia Jimenez for micro-Raman analysis, and Campos for technical support in profilometry measurements. We would also like to thank Jimenez, Vasquez, Cedillo, Novello, Pompa, and Gonzalez. Thank you very much for your attention.